All right, hi everyone. We're going to be starting in around a minute. I think someone asked what happened to the week 1 homework. I think it was uploaded on the website. Hi, hi everyone. All right, we're going to be starting right now. First we have we're going to be going over something pretty big. I think you guys got an email about this earlier today. But first we have a new point system that we've been talking about for a while. But I think Rich sent out an email earlier today detailing how you can get points and what exactly you can do with them. So you can, in order to get points, you basically do something cool by, for example, attending class or doing your homework or helping us like reach more people. And then you can earn points by filling out a form. And then after you earn points, you can attend special sessions that we have planned. For example, you can see 4 that we have planned on the side. The timing is still TBD, but you can start planning out which ones you want to attend. And also besides attending special sessions, we also have a leaderboard for people who have the highest amount of points. And if you get into the top of the leaderboard, you get a few prizes. So that's pretty cool, I guess. The second announcement that we have is we have a math tournament that we're going to be hosting next week. So it's going to be around AMC 10 difficulty, and everyone is allowed to join. So if you have friends who aren't in Kid Teach Kid or they're not enrolled in Kid Teach Kid, you can also encourage them to join as well. Yeah, and also you can earn points for participating and also winning in the top like 10. So that's that. Yeah, so let me know if you have, I think Rich is going to send out another email detailing the Flash Math tournament. It's not going to be an old AMC test. We wrote all the questions ourselves, so don't worry about that. All right, we're going to be starting today with some vocab for public health. All right, so last time, remember we stopped at an outbreak investigation that I told you guys to start thinking about. So today we're going to be starting off prefacing with some important key concepts that you need to know for public health. So first of all, we have an outbreak, and an outbreak is probably the most used terminology. It's basically more than expected cases over a short amount of time over a specified geographical time period. So for example, if let's say we have around 10 cases normally in an area, and then suddenly around 2 days there's suddenly like 40 cases, but this is only in like a small place, for example, a city, then that would be considered an outbreak. But you need to remember that it must be more than expected and it must be over a small area, over a specific time. So someone is saying like COVID, well, an example for COVID I would give is when COVID was in its initial stages in Wuhan, before it like propagated elsewhere, that would be an outbreak. But once it propagated, it becomes an epidemic. So the difference between an outbreak and an epidemic is that an epidemic is much wider in its geographical area. It could be a country, multiple states, multiple cities. So basically it's a large scale outbreak, but it still has to do with a short period of time and a specific geographical location. So next we have a pandemic. So a pandemic is basically another large scale epidemic. So this one could be over many continents, several countries, etc. So like COVID-19 right now, that would be an example of a pandemic. Okay, so next we have endemic. You may have realized that outbreak, epidemic, and pandemic were all related to diseases in an abnormal condition. So normally you would not be expecting an outbreak or an epidemic or a pandemic, but an endemic disease is one that is constantly found in a location. So it's the baseline level of a disease That's usually a synonym for endemic. Is the flu an endemic? Well, that depends, because sometimes like a lot of diseases are actually endemic, but it actually depends on the endemic level. The endemic level is known as the baseline. So for example, the common cold would be endemic, but polio would not be endemic. So during flu season, flu would technically be counting as endemic. So yeah. All right, and then we have hyperendemic. This one just means that it's endemic, but in high amounts. So for example, in sub-Saharan Africa, malnutrition would be hyperendemic because it's always there. Well, sadly, it's always there, and it's usually found at high amounts. And finally, we have sporadic, which is basically the opposite of hyperendemic. It occurs irregularly and infrequently. So for example, if there is a case of histoplasmosis, which is a very rare fungal disease, it rarely does not happen, but once in a while it may occur. So that would be an example of a sporadic disease. Okay, let me check Q&A real quick. Someone asked, would an epidemic generally only apply to a country or a city? An epidemic would generally apply to a country, but if it's a large city, for example, New York City, and it spreads like around New York, then it could also be considered an epidemic. Someone asked, where's the website? Just go to kidteachkid.org, and there should be a tab on class resources. Okay, yeah. Okay, let's move on. So now we're gonna talk about R0, also known as R0, also known as the basic reproduction number. So this is probably the most important concept in epidemiology. So every single epidemiologist knows about R0, and if you want to learn more about public health, you have to start off by knowing exactly what R0 is and what it symbolizes. So as you can see in the definition here, the R0 is the number of secondary cases produced by a single primary case in a completely susceptible population. So what that means is, let's say Joe has disease X, and Joe is just going about his day, and on average, like across a period of time, on average, he transmits disease X to 5 other people. So if everyone who had the disease can transmit it to 5 other people, and assuming that all those people, all the rest of the people in the population are completely susceptible, then the R0 of disease X would be 5. So what that means is the diseases with a very high R0 value, for example, measles, I think I talked about that last time, where measles is like very, very high. Measles has an R0 value of 15. So that's like extremely high. So if there's a measles outbreak, then the town is like pretty much screwed. So yeah. Someone asked, okay, COVID is not as high as measles. COVID is like around 5-ish, I think. But I think recent studies have placed the R0 of COVID to be around 3. So we don't really know yet, since everything is still like under investigation. All right, so what exactly does the R0 tell us about a disease? So, well, it was 5.7, but I think there are new studies that are coming out that are placing it at a lower range. So yeah, okay. So if the R0 value is greater than 1, for example, like the flu is usually around like 1.3 or something. COVID is like 2 or 3 is like I think they like changed it recently, but I'm not sure. So we're not going to use that example. Measles is around 15, chickenpox is around 8, things like that. Those diseases have a very high possibility of spreading in the population. So if public health officials do not help place quarantine measures or help treat people, then it can spread very, very high, very, very far. Okay, let me see. All right, so now someone asked, would R0 apply to COVID-19 with a single person who spreads it to others? I think you're misinterpreting like the exact definition of R0. So R0 would be the average of all the people who spread the disease, like the average number of secondary cases generated by a single primary case. So it wouldn't be targeted to a specific person. Okay, So now we need to talk about something called herd immunity. So you may have heard that around like this pandemic, people talking about, oh, herd immunity, we need to optimize herd immunity, things like that. So what herd immunity means is that if a lot of people in a population are immune to a certain disease, then it will prevent everyone else who is susceptible from getting the disease. So for example, let's talk about the flu again. If a lot of people in the population get the flu vaccine and basically if a lot of people get immune to the flu, then it'll cause people who don't have the, who aren't vaccinated to also be immune to the flu just because of the protection that they receive from other people. So as you can tell, a disease that is easily transmissible, for example, measles. I think I'm just always giving the example of measles because it's like a very extreme example. So yeah. So measles, it will be hard to control even if the most of the population is vaccinated because it's so transmissible. But on the other hand, if you have a disease like that's not as, it's not measles, it's measles. Not as transmissible like the flu. The flu only has like a R naught value of around 1.3, I remember. Here, I'll just type it in the chat. Then you don't need as many people to be vaccinated in order for herd immunity to work. So how do you exactly calculate what % of the population needs to be vaccinated in order for herd immunity to work? So that is why we use something called the herd immunity threshold, which is also called HIT sometimes, like HIT. So what you would do is 1 minus 1 over R naught. So let's just calculate the herd immunity threshold for COVID using the R naught value of a 5, even though it may not be completely accurate. So let's just say we use the R naught value of 5, we have 1 minus 1 over 5. So that would be around 80%. So around 80% of the population needs to be vaccinated in order for the entire population to be protected against COVID. Well, that is a very large number. So that's why we need to use a lot of quarantine measures and social distancing to prevent it from having to get to that stage, basically, state. Okay, let me check questions real quick. R0, it's R0, not RO, just letting you know, because it means R naught, not as in like NAUGHT, so yeah. Also, how is R naught used when it would be used as in like there is 30 R naught? What do you mean by that? I'm not sure what you mean by that, Dan. Yeah. Okay, I'm gonna pause the chat real quick because people are telling me to. All right. Next, we're going to go to the review of our outbreak investigation that we left on last time. So you can go ahead and read this again just to refresh your memory. Yeah, I'll give you like around a minute to read that. Okay, I think you guys probably have read that by now. So if you can tell, this is not a good situation to be in because first of all, it affects children and teenagers. Second of all, the symptoms are pretty like severe. You can see that there's going to be diarrhea, vomiting, fever, abdominal cramps, even though abdominal cramps doesn't seem to be that bad, but fever is pretty bad. And then you can see that within this past week, you get a lot of cases. So what if the next step to figure out exactly what's going on is to try to classify it as one of these: outbreak, epidemic, or pandemic. So type in the chat which one you guys think this situation would be. Okay, I see a lot of outbreaks, which would be right. If you said outbreak, then that would be correct because it's in Seattle, Washington, and it's just Seattle. So think about it. Seattle is a city, so it would be pretty localized. So that's why it would be an outbreak. Okay, so now let's look at this. Okay, so the first thing we will do is after we figured out that it's going to be an outbreak, we have to try to find more cases. We have to try to gather as many people as we know who have the disease so we can get more information. Well, okay, I know it says outbreak in the title, but outbreak is more of like a holistic term that accompanies outbreak, epidemic, and pandemic. So that's why I still wanted you guys to know. Okay, now we have case definitions. So basically, as I was saying, we need to find more people with the disease. So in order to do that, we have to write a case definition. What that means, basically, it defines the terms for someone to be classified as a case. And if you don't know, a case basically means someone with the disease. So, all right, so now let's look at what we need to have in our case definition. So we need to have person criteria, place criteria, time criteria, and clinical information criteria. So by person criteria, what that means is we need to have specific aspects that all the people seem to have in common. So let's look back in here. We can see that it says you've been receiving a ton of emails and calls, and they tell you that they've seen many children and teenagers with this disease. So our person criteria would be children and teenagers. So just keep that in mind. Next, we got to look at our place criteria. So place criteria would be things that have to do with the location. Well, that's pretty obvious, but let's just look back and we can see right off the bat, Seattle, Washington. So that would be our place criteria. Also keep that in mind. Next, we have time. The time of our outbreak is the week of August 12th. So that will be our time criteria. And finally, we have clinical information. So this one is not as straightforward, but basically it just means things having to do with the disease. So like properties of the disease. So let's look back in here. We can see the properties of the disease are diarrhea, vomiting, fever, and abdominal cramps. So we have all of those figured out. So we have all the things we need to write a case definition. And on the other side, we have different types of case definitions. There are three: susceptible, suspected, probable, and confirmed. So suspected is they might have the disease, but you're not sure at all. Probable is they most likely have the disease. And confirmed is they 100% have the disease. And this can only be achieved by running laboratory tests and finding out that they are confirmed to have the disease. So let's take a look at examples of case definitions. So what do you think the case definition on the very left would be? So type it in the chat. Which type of case definition? Okay, I'm seeing a lot of suspected, a few probables, but basically this would be suspected. Why? Because it says has experienced one or more symptoms. Notice how vague that is. Either you can, just by having abdominal cramps, then you fit this case definition. So it's very broad, it's very vague. So that's why it would be, it's suspected. But on the other hand, let's look at the second one. You can see that the second one says, has experienced 2 or more of the following symptoms: bloody diarrhea, fever above 39 degrees Celsius, vomiting, and abdominal pain. So you can see that this is a lot more specific. So yes, this one would be probable. And notice that the symptoms are also very specific. So instead of just saying diarrhea, we have bloody diarrhea. Instead of just saying fever, we have fever above 39 degrees Celsius. And we can see, instead of just saying 1 or more, we have 2 or more. So this is why the second one would be probable, and the last one would, of course, just be confirmed because that's the only one left. And also, you can see that it says has laboratory confirmation of E. coli in their stool. So that should be like the key to figuring out that it's confirmed, because there's the words laboratory confirmation. So yeah. Good job, everyone who participated. So let's move on. Actually, before we move on, I just wanted to say, so in the very early stages of an outbreak investigation, you can only write a suspected case because you don't really have that much information about the disease itself. But as you progress on, you can start writing probable cases. And then once you start getting enough resources to conduct lab tests, then that's when you can also start writing confirmed case definitions. So yeah. All right, so now let's move on to line listing. So if you recall, the entire subject of this week will be collecting epidemiological data. So line listing is just one way to collect epidemiological data. So as you can see, here I have a line list. So on the very first column, you have the case, gender, age, etc. You can see on the right half, you have everything about their symptoms, which in this case would be their clinical information. Notice that in this line list, I have information about person, place, oh no, sorry, not place. Sorry, I didn't put place, but I have information about person, time, and clinical information. So person information example would be initials, gender, and age. Place, well, I didn't really put that, but usually you would put that. Sorry about that. Time would be date of onset. You can see 12th of August, 13th of August, etc. And then clinical information would be all these yes, no's, diarrhea, fevers, stuff like that. So yeah, so whenever you're trying to write a line list, you want to make sure that you include the information from your case definition to classify all the people that you think possibly will have the disease. So any questions as of now? Dan Bond is asking, which are we talking about now? We have been, for the past while, we have been talking about this outbreak investigation. Sorry, I think the screen is kind of lagging, but yeah, this one, where you see that there's a bunch of cases going on in Seattle and during the week of August 12th. Okay, you know what, since y'all have not been spamming me, I'm gonna open the chat up again, but if you're gonna spam me again, I'm just gonna close it. Okay, because I like for you guys to talk amongst yourselves when I'm asking these questions. So yeah, hopefully you got another good look at what exactly we're dealing with, Dan. Okay, now we're just gonna move on to something called Epi Curves. Epi Curves are way more important than line lists. They're probably the most important part of an outbreak investigation, if not, well, one of the most important parts. So notice something about these Epi Curves that I have on the right. So notice that each one of those bars represent the number of new cases per day. So not the total number of cases, but the new number of cases. So let's look at the A, which says point source. You can see that it goes up and then just immediately goes down. And then continuous common source, you can see that it like keeps going across, like, but it only goes down after a long time. And then you can see intermittent. We're not really going to be talking about intermittent. It's not that important in an outbreak investigation, but we are going to be talking about propagated. So you can see that there's so many different peaks in propagated. It goes like up and down, then up and down. Yeah. So the reason behind it going up and down is because there's person-to-person spread. So for example, COVID, the first people who get COVID will spread it to the next people who get COVID. So the first people who get COVID will represent the first peak, then the second wave of cases, the second peak, then the third peak, etc. Someone asked, why isn't it a line graph? Okay, in a line graph, it's not as easy to see exactly how many new cases there are every day. That's why we use something like this. And these are not exactly bar graphs. These are called histograms. The reason is because we are looking at time intervals on the x-axis instead of like very discrete intervals. And also they're connected to each other, which also helps it become a histogram basically. Okay, so let me just give you a quick overview about point source, continuous common source, and propagated outbreaks. So point source, as you can see, is a characteristic of an outbreak in which there is little person-to-person spread. So there's one source of contamination, people get it, and then they don't spread it anywhere, and then it's gone. So you can see the curve going like up and then immediately down. Continuous common source, there is still one source. That's why it says common source. But public health officials don't know where it's coming from. So it just keeps infecting a lot of people. That's why you can see that it's continuous. And on the other hand, you can see propagated where it goes up and down as I was talking earlier. That's because there is person-to-person spread. Okay, now let's go back to our case, our outbreak investigation. Remember this. Now I went ahead and drew a histogram or a Epi curve for our outbreak investigation. So this was basically based on information from the line list. I added a few more days, but I basically translated the information from the line list into this Epi curve. So let me know which type of Epi curve you think it is. Is it point source, continuous common source, or propagated? Oh, that's actually a great question. Someone asked, what does Epi mean? Epi actually just stands for epidemic. So just that's the short part. What if a disease doesn't have does not have any symptoms, that means the disease is asymptomatic. So yeah. Is the case number the order of people who called? We're going back to the line list. You can see, yes, it is basically based on the date of onset. So hopefully that answers your question. All right, anyway, back to this. Did you guys enter what you thought it was? Okay, somebody just put a huge space, so I can't really see. So go ahead and type it in again. Let me know which type of outbreak. Yes, people are saying point source, and that is correct. The reason behind that is it just goes up and then it just immediately goes down. So yeah. And why is it point source? It's because once someone gets E. coli, it's rare that they're going to spread it to someone else, since E. coli is transmitted through fecal oral spread. What that means is someone has to come into contact with someone's, like, an uninfected person has to come into contact with an infected person's feces in order for them to get it. So that's like pretty rare. So that's why it's like point source. Hopefully that makes sense. All right, next we will talk about incidence. Okay, so incidence, you can see it here as I wrote, incidence equals new cases. So what that means is, for example, in this Epi curve, the incidence of E. coli on August the 15th would be 11 cases. Meanwhile, you can see that the incidence on August the 18th is 13 cases. So it's basically, it refers to the new cases. But just talking about how many new cases show up is not that helpful for epidemiologists. The reason is because, let's say there's like a very rural area in which there's only like around 100 people. And just looking at this, you can see that if there's 16 people out of 100 people who get the disease newly, that's much more severe compared to if there's a large urban population that has like 10,000 people and there's only 16 people who get it. So just looking at the number of new cases will not tell us much. So we have to compare it to the population size. That's why we use something called cumulative incidence, in which we take the number of new cases divided by the person. Oh my God, what are you even doing? I am reading the chat here. Anyway, you divide it by the number of persons at risk, and then you divide it by the period of time. So for example, oh yeah, I think someone got mad at me for using Bob and Joe, so I'm just gonna use someone else. Oh, someone asked, does the symptoms affect the graph, like mild and stuff? No, symptoms do not affect the graph. So as long as you are a case, then you get listed as a case, and you get graphed on the Epi curve. So that's, yeah. All right, anyway, I think we were here. So let's think about it. Can you calculate the cumulative incidence of the outbreak if the population at risk is 10,000 people? So let's look at what we can do here. So let's go ahead and count how many cases there are. You can use a calculator if you want. I'm probably gonna use a calculator, and count how many total new cases there are. And let me know and write it in the chat when you're done. Okay, let me know if you're done. Whoever that is, you only stop spamming me with Chinese words. Okay. Yes, I think the total should be 77. For those of you guys who are getting 77, good job. So let's look at how to calculate incidence with the 77 that we got. So let's plug it into the formula. Basically, we're not gonna talk about incidence rate. Incidence rate is more of an advanced concept. If we have time at the end, I'll talk about it. So we'll just talk about cumulative incidence first. So take the number of new cases, which we just calculated was 77, divided by the number of persons at risk, which I just told you down here is 10,000 people, and then divide it by the period of time. And the period of time you can see would be 8 days. So let me know what you guys get for the cumulative incidence and type it in the chat. Okay, I see y'all are doing well. Okay, someone asked, what if a disease doesn't have any symptoms? Even if a disease doesn't have symptoms, there is still laboratory testing material. So for example, I can't really think of one right off the top of my head, but there's this disease called Salmonella typhi, where there was this one lady who spread it to a bunch of people. I'm sorry, I'm going off a tangent, but y'all calculate while I tell the story. So there was this one lady who was a carrier of Salmonella typhi, meaning that she, even though she had it, she did not show any symptoms. Yeah, typhoid Mary, good job. So she transmitted the disease to a bunch of people, but that's actually, I don't think that's a great example, but let's just say there's a disease like typhoid, like Salmonella typhi, where a lot of people don't show symptoms. Well, they can still get tested and the test will still come back positive for Salmonella typhi. So that is why they will also still be included in the white list. So hopefully that makes more sense. Okay, y'all are getting the right answer, I think. It should be 0.0009625. Okay, but the thing is, it's like kind of awkward to write the cumulative incidence as 0.0009625, number of new cases per persons at risk per day. So what we can do is we can multiply this by 10,000 to get a new incidence of 9.62. Wait, let me think. Yeah, 9.625 new cases per 1,000 persons at risk per day. Does that make sense? Let me type it in the chat real quick so y'all can see. I think it was 625. 9.625 new cases per 10,000 persons at risk per day. So that would be our final cumulative incidence. Okay. Let me know if you have any questions. Okay, let me check the Q&A real quick. Is the Epi curve of coronavirus propagated? It should be. The reason behind this is because, yes, yeah, let me answer one question at a time. So the Epi curve should be propagated because there are various, there's ways for you to spread it between each other. So for example, if you just go to like a COVID Epi curve page, for example, I use worldometers a lot, you can see the different peaks and stuff. All right, so you only asked persons. Yes, in epidemiology, saying people can be kind of like, it's like not as formal as saying persons, even though that may be kind of weird since we're all used to saying persons, but it's a real thing. I promise I'm not like trolling or anything. Okay, next we're gonna move on to something that's not incidence, it's prevalence, but the concepts are kind of similar. Prevalence, instead of referring to new cases, prevalence refers to existing cases. So what that means is, let's look at this Epi curve again. So on August 14th, tell me, write in the chat how many existing cases of E. coli there are going to be on August 14th. I see a lot of 8s, but keep in mind that 8 is the number of new cases on August 14th, but we want the number of total cases. So how can we get the number of total cases? Go ahead and think about that a little bit. So I'm seeing a lot of 15s, and that would be correct because we can see that on August 12th, we have 2 cases. On August 13th, we have 5 cases, and on August 14th, we have 8 cases. So adding them together will give us a total of 15 cases on August the 14th. So the prevalence of E. coli on August the 14th will be 15, but remember, as I said, we don't really like just plain numbers. We want to compare them to the population. So that's why we would use something called point prevalence. So point prevalence, we would take 15, which is the existing number of cases during a certain point in time, divided by the population at risk during a certain point in time, which would be, again, 10,000 people. So yeah, that would just be our prevalence basically. And period prevalence is the existing number of cases during a certain period of time. During a certain period of time rather than a certain point in time. So let's move on to back to here. Tell me what is the period prevalence of the disease between August 14th and August 16th. And it's probably easier than you think. It's more straightforward. So just let me know what you think the period prevalence is between August 14th and August 16th. What was okay, the formula was here. Take the number of existing cases during a certain period or point in time and divide it by the population at risk. Okay, so so basically in order to find the period prevalence, we would have to find the number of existing cases between August 14th and August 16th. So we know the number of cases on August 14th, as we calculated before, was 15. We got 11 new cases on August the 15th. So that would make the total number on August 15th to be 26. And then we got 16 new cases on August the 16th. So that means the period prevalence would be 42. So notice that the period prevalence between 14th and 16th is basically just the point prevalence at August the 16th. But yeah, that's just a different way of calculating prevalence. And the same thing goes, you would just do 42 divided by the population at risk, which is 10,000. So good job, Emily. Let me see if anyone else got it. Well, yeah, okay, good job to y'all who did get it. Okay, can you calculate the point and yeah, we just did that. All right. Does anyone have any questions? Oh, okay, someone said I'm going too fast. Okay, I'll go slower from now. I'll just repeat what I just did. I'm so sorry. So what I just did earlier was I found the point prevalence of E. coli on August the 14th by adding 2 plus 5 plus 8, which got me 15, and then divide that by the population at risk, which is 10,000. So it would be 15 cases per 10,000 persons at risk, basically. That's the point prevalence. But the period prevalence, I would have to add 15 plus 11 plus 16 in order to get 42. So the period prevalence, I would have to take 42, then divide it by the population at risk, which is still 10,000. So that's why the period prevalence would be 42 cases per 10,000 persons at risk. Does that make a little bit more sense? Okay. All right, I'm gonna open up the chat. Okay, thanks. I'm gonna open up the chat again, but if you spam, I'm gonna close it up again. Okay, we have around 20 minutes left, so we're good on time. So next we're gonna move on to study designs. And study designs, we're already going a little bit into what is the topic of next week, but since we still have time, I'm just gonna go over them. Study designs is no longer collecting data anymore. So everything we did above, so from the incidence, prevalence, Epi Curves, line list, that was all collecting data. So study designs, we will start using them to analyze data. So let's just look at this little graph that I have here. But before we do that, let me talk to you guys about why we use study designs. So we know that there's an E. coli outbreak in Seattle. This is just hypothetical, by the way. I literally just made it up. But we need to try to figure out a way to stop this outbreak because that's our whole goal. But in order to do that, we need to figure out what is actually causing this outbreak. We don't just want to be like randomly telling people to not go to a certain restaurant when we don't even know that it's actually causing that it's actually causing the disease. So we don't want to be like randomly targeting things that aren't actually the source. So we use study designs to determine exactly what the source is. So let's look at this. Let's look at the left. So we have experimental, in which we have a randomized controlled trial. So this is probably, you're probably familiar with this from your science class. When you're doing an experiment, you probably have like independent variables, dependent variables, you're changing some stuff around. But this is not the thing that we're actually going to be using. Instead, we're going to be using something called observational studies. And the difference between an experimental study and an observational study is that in an experiment, the researcher is actively changing variables and assigning certain people to certain groups. But in observational, as the name says, you're literally just observing. You're observing everything unfold in front of you. So what that means is you, people, for example, let's say you want to determine, same scenario, I'll give you, ways that you can use an experimental study and an observational study. So an experimental study, let's say you want to determine the effects of classical music on a person's classroom grades. So for example, that was actually my AP psychology prompt. But basically, the researcher wants to determine whether listening to classical music when studying can help a person get better grades. So what they would do is they would get one group of people to always listen to classical music when they're studying, and another group of people to not listen to classical music when they're studying. And they would let them do what they do, take tests and stuff, and then at the end, they will average the grades of the group 1 and then the group 2, and then figure out whether there's a correlation. So that would be an experimental study. But observational study, on the other hand, you wouldn't be telling people to listen to classical music or not listen to classical music. You would just take people who just usually do listen to classical music, like they're used to doing it, and then you would take people who are not used to do it, and you would and then you would follow them across time and then compare their grades. So notice the difference here. You're not assigning people, you're not telling them to listen to classical music, you're just following people who just choose to versus they choose not to. So yeah. Oh, and I'm not sure what your Tian Chen, I think. They listed a good point, but some people are just smarter. That is a good point, but that's why you use a tool called randomization in experimental studies. You randomize people so that smartness per se is not a factor, but again, you can't really do that in observational, which is why most researchers prefer experimental. Okay, so now that you have a good example of that, let's move on to the next slide. Oh, this has been perfect. I forgot I put this slide here, but basically, you want to test the relationship between playing classical music during studying and the performance on a test. How would you do this? So the independent variable is basically the variable that you control. So type in the chat. I'm going to open up the chat. Oh, wait, it is open. Sorry. Wait, is it? Oh, yeah, it is. Okay. Type in the chat what you think the independent variable of the study would be. And just letting you know, the independent variable is the variable that you change. Yeah, so classical music or not, the music, that's basically right. Yeah, y'all are right. So now let's talk about, good job everyone who said classical music. Let's talk about what the dependent variable would be in this situation. So type that in the chat as well. Dependent variable is the one that you can see. That's not the one that you change. Yes, test scores would be correct. The experimental group is the group that is undergoing the certain thing per se that you want to test. So let me know which group would be the experimental group. Type it in the chat as well. Yes, the group where the students are listening to music, that is perfect. That is the experimental group. And on the other hand, type in what the control group would be. It's basically the non-experimental group. So just type it in the chat. Students without listening to music. Good job, everyone. So randomization, as I was saying earlier, you would make sure that you're not just putting all the boys together to listen to classical music and putting all the girls together to not listen to classical music. You don't want to do that because there could be inherent biases in people who listen, in boys versus girls, or a certain type of people versus not. So you want to randomize. So you could use a die, you could assign everyone a number, and then you could roll the die and then see whichever person goes into which group. So that's that. Or you can use a random number generator. So things like that. That's how you can randomize the groups to, oh, I'm so sorry. I did not mean to be sexist. I was just saying that, like, never mind. But basically, you could use a random number generator to determine who would be put into which group. So that would be an experimental study. So let me know, do you guys think we can use this experimental study on our outbreak investigation? Yes or no? Yeah, let me know if you think we can use an experimental study on our outbreak investigation about E. coli. Okay, okay, yeah. A lot of y'all are saying no, which would be the correct answer, because think about it. You can't just tell people you must eat at this restaurant, like, and then tell another person, another group of people, you can't eat at this restaurant. Because what if the restaurant actually is the source of the disease? You can't just force people to go eat something that's contaminated, which is why it would be unethical to use an experimental study for this outbreak investigation. So now we're just going to move on to instead we would have to use an observational study for this outbreak investigation, which is something we'll get into next week. All right, next, we're going to talk about the strengths and weaknesses of experimental studies. So the strengths is, oh my God, I accidentally put the wrong, okay, never mind, we're not talking about this. I accidentally put the wrong thing, but basically, don't just ignore this, by the way. She was wrong, okay. Sorry about that, but basically I'm just going to talk about a few positives. The experimental studies are very scientifically sound. So if you're trying to prove something, cause something, then using an experimental study would make your study very accurate, per se. But on the other hand, a disadvantage of an experimental study would be that it costs a lot of like money and time. So it would take you a lot of time to follow them up and see how, or like their whole like grades and stuff if we're using the classical music thing, or it'll take a lot of money to try to like convince people to enroll in your study, things like that. So that's not very good for experimental studies. Another bad part of it is that it's not always ethical, as we saw in the example of the outbreak investigation. So yeah, those are some good things and bad things about experimental studies. So yeah, let's move on to our outbreak. Oh, I think we already talked about this. Should we be using the experimental study? No. Why or why not? Because it's unethical. And finally, we've already gathered all the data and we will continue with this outbreak investigation next week. So thank you, everyone. Now it's a Q&A time. Let me know if you have any questions. And for those of you guys who are also attending my biology class, you can get up and like stretch a little bit. We're going to be starting at around 5 o'clock. Yeah. Oh, Chelsea asked, what does prevalence do? Okay, so that's a great question. Prevalence is the number of existing cases. It gives epidemiologists a good understanding of the burden of the disease in a population, if that makes sense. Like it tells you, like, I don't know, what's a better way to say burden? I think you understand what I mean, right? The burden of a disease in a population. Okay, let me check Q&A. Talk about COVID-19. I will talk about COVID-19 in week 4, so tune in on week 4 for that. Grace asked how many people are here. There's 90 people here. Someone asked, can you leave? If you're not taking the biology class, then feel free to leave. And thank you all for coming to the public health class. Goodbye to everyone who's not taking biology. And if you're taking biology, I will be just gonna transition into that real quick. Oh, Jacqueline asks, I mean the parts of coronavirus like its RNA and others. No, we're not really going to be talking about like the nitty gritty like details of COVID, but that is something that we might be covering in biology class. So